In this video, I'm going to talk about the difference between delta G and delta G naught. We have the relationship that the change in Gibbs free energy is equal to the standard change in Gibbs free energy plus R, the gas constant, times T, the temperature, times the natural logarithm of Q, where Q is the reaction quotient. So if we have some reaction, A plus B, going to 2C plus D, then our reaction quotient Q is equal to the concentration of the products raised to the exponent of their stoichiometric coefficient. So for C, this is C to the power of 2, and D is just to the power of 1, over the concentration of our reactants. This looks very similar to our definition of the equilibrium constant. However, for the equilibrium constant, these concentrations are the concentrations at equilibrium. For Q, it's our concentrations for wherever our system is at the moment, whether it's at equilibrium or not. When these concentrations are equilibrium concentrations, then Q is equal to K. So for delta G, at equilibrium, we know delta G is equal to 0. So if delta G is equal to 0, and that's equal to delta G naught plus RT ln Q, then we can solve out and say that delta G naught is equal to negative RT ln Q. Now, because we're at equilibrium, this Q is actually a K. So I'll replace that and say this is negative RT ln K. This equation holds not just at equilibrium, but all the time. No matter what the progress of the reaction, delta G naught is equal to the negative gas constant times the temperature times the natural logarithm of the equilibrium constant. So K is equal to, for this reaction here, C squared times D over the concentration of A times the concentration of B. And these concentrations here are the concentrations at equilibrium. So if we look at this graphically, we can imagine some graph where here we have 100% reactants, and on the far side we have 100% products. So on the reactant side, that's fully A and B, and on the product side, that's 2C plus D. And we plot this against free energy. Let's say our reactants start at low Gibbs free energy and the products are at high Gibbs free energy. Well, we know that the equilibrium constant, K, relates somehow to delta G naught. In this graphical representation, at standard state, this difference here would represent delta G naught. So that is the difference between the Gibbs free energy of the pure products at standard state minus the Gibbs free energy of the pure reactants at standard state. Now, if you recall from the derivation of Gibbs free energy, delta G is equal to negative T times the change in entropy of the universe. We know that a higher entropy is associated with a state that's more probable. So we're always increasing the entropy of the universe in a spontaneous process, which means we're moving towards a more probable state. Because of this negative sign here, that means that lower Gibbs free energies relate to the more probable state. So in this case, our reactants are more probable because they have a lower Gibbs free energy, and our products are less probable. However, the products still have some probability, so we'd expect some of them to still be present at equilibrium, but because the reactants are more probable, we'd expect it to be primarily reactants. So we could imagine that our equilibrium value might lie perhaps here, where we have 75% reactants and 25% products. So let's say that this is our equilibrium value. And then we can draw in this curve here. Now, delta G naught, it doesn't matter where we are along this line, delta G naught's always the same because it's always pure products minus pure reactants. Delta G, however, changes with the reaction progress. So we can look at the slope and get an idea of what the sign of delta G is. So if we look at the slope here, where we have mostly products and just a little reactants, the slope is negative. Because the slope is negative, that means the reaction up here is spontaneous in the forward direction, and so our reaction will progress towards products, so towards the right-hand side of this graph. We keep progressing with this negative slope until we hit this point right here. At this point, delta G is equal to 0. That means that either going to the right or to the left, would involve an increase in Gibbs free energy, which would relate to a decrease in the entropy of the universe. So that's not going to happen. Our system is stable, it's at equilibrium, delta G is equal to 0. If we were to move past that point, so if we were to have more products than reactants, like here, then our slope is positive. All of a sudden, the forward reaction is no longer spontaneous, but the reverse reaction is. So going back from C and D towards A and B is spontaneous. So our reaction would move this way, which is towards reactants, towards the more probable state. And we keep moving that way again until we got to this equilibrium value. So you can see that where we are on this curve, as in whatever the progress of the reaction is, has an effect on delta G, but not on delta G naught. So delta G naught gives us an idea of where our equilibrium is going to lie, and delta G at any point in the reaction, the sign of delta G is telling us whether our reaction is spontaneous, that is if delta G is less than 0. If it's not spontaneous, so delta G is greater than 0, in which case the reverse process is spontaneous, or when delta G is equal to 0, our reaction is at equilibrium.